Hi, this is Keith Saver, doing my final project presentation for deep learning on reinforcement learning for games and simulations. So the purpose of this project is to analyze the effects of adjusting the learning rate of a neural net used in reinforcement learning. DeepQ networks are used here. They've been shown to be effective in games simulations. Um, DeepMind has used them very effectively to learn Atari games. In here, the OpenAI Gym is used to supply a variety of standardized learning environments. So some questions to dig in here are: how does changing the learning rate affect the model's ability to converge on an effective strategy? And does changing the learning rate affect training differently in more and less complex environments? DeepQ networks are a form of reinforcement learning. DQNs rely on learning values or rewards that occur when specific actions are taken in certain states. So by eventually, over time, associating positive and negative rewards with performing different actions in specific states, the DQN can slowly learn effective strategies to maximize rewards. So just to note, DQNs do take generally a very long time to train. They can struggle to converge onto a correct strategy. Since they just rely on sort of the slow association of rewards and states and actions, that's why they take so long. In many game simulations, also, the model may encounter very similar situations for an extended period of time. As you're playing a game, you're going to be perhaps in a similar situation for a while. This can result in a temporarily biased training set, effectively. So this is why also, the model can take a long time to train. Due to the large amount of data required to effectively train these models, they are most effective in games and simulations, since game simulations can, of course, effectively create infinite data with procedural generation just by playing the game. So the hardware here is Windows 10 with an i7 and 32 gigabytes of RAM. The software here was Python 3.6, TensorFlow, Keras, the OpenAI Gym. And one note here is that a number of the OpenAI Gym packages are not made to be compatible with Windows. I did find an Atari Pi Windows fork, so that here allowed me to run the Atari simulations on Windows. I was not able to run all of the OpenAI Gym environments on Windows, but this still supplied me with enough environments to work with here. All right, so a little bit more about the OpenAI Gym environment. So OpenAI developed Gym in order to aid reinforcement learning research. So one difficulty with comparing reinforcement learning algorithms has historically been a lack of standardized testing environments. OpenAI Gym was made to help solve this problem by supplying an easy method of training with a large number of environments that anyone can easily access. So the information passed to and from these environments does vary slightly by environment. For example, with some Atari games, either RAM or pixel data, but they do follow the similar general pattern. The environment gives a state, the model can pass in an action, and then the environment returns a new state, a reward, and whether the assimilation has been completed or not. So that means, for example, whether the game has been lost. Then this standardization of information passing does allow for reinforcement learning algorithms to be compared across environments by running the exact same algorithm on these different environments. So this is very useful for comparing the effectiveness of different algorithms on different kinds of environments. So here, I selected 3 different OpenAI Gym environments. The first is a very basic cart pull. So basically, you're controlling this little cart here, and then it's trying to balance this pole on top. So the cart has to either move left or right at every instant in time, and then gets points for how long it keeps the pole standing up. The game is lost either by letting the pole fall too far to the sides, or when the cart goes off the left or right side of the screen. Acrobat here. So there's a couple basically hinges and lines. So this hinge right here is held steady. This hinge is controlled by the model or by input, and then the goal is basically to get this line up here, this blue bit, to touch this line up here. So you're trying to swing it up here. And then Space Invaders, if you haven't played it, basically you're controlling this little ship at the bottom. You can move left to right and shoot upwards. These alien ships slowly move side to side and downward, and they are also shooting at you. The goal is to shoot these ships before they shoot you and prevent them from getting to the bottom of the screen. All right, so here going into the DQN model implementation. So this model my implementation was based off of some implementations I found from other people online. So, for example, people making OpenAI Gym tutorials. I did adjust a number of things that I will discuss throughout here. So you can see here I made a list of the environments and then the learning rates to test. And then some notes here as I increased the batch size compared to many other implementations, and then I also slowed down the rate of decay. So as with reinforcement learning algorithms, as discussed in the lecture, there's sort of this exploration versus exploitation trade-off. And so here I decided to increase early exploration. This discount rate here is used to sort of discount future rewards versus getting immediate rewards. The model prefers to get rewards now, but obviously still very much values future rewards. So that's what this discount rate is for. So here we have this class that's implementing the DQN algorithm. So there's some changes here as I forced the learning rate to be passed in. Obviously, since I'm trying to compare learning rates here, so the instance of the model needs to have this learning rate. I also increased the neuron counts. The reason here, and also with the increased batch size before, is given the complexity of Space Invaders, I very much struggled to get any meaningful training. And so I was hoping by increasing the neuron counts here and so adding some complexity to this neural net that I'd get some more meaningful training. So basically, this remember function, we can go up here, we can see this state memory max of 1 million. So this model basically remembers up to 1 million states at a time. And so in this replay function, what it does is the model will go back and look at 50, because batch size here, which I set to 50 before, look at 50 of these states that is remembered, and then train on these, basically trying to predict rewards. And this is how the model learns. And then here, this act function is how the model decides on its action. So at the top, you see the exploration section. So basically, this is the randomization. And then here we sort of see the exploitation section where it's trying to estimate the reward values for all possible actions it could make, and then return the action that would maximize its rewards. So it's basically, this is the trying to maximize its rewards. All right, so then this function here actually plays the environments with all the learning rates. So we can see here these 2 for loops at the top, for each environment, for each learning rate. So this creates 9 environment learning rate pairs, 9 runs, runs 500 episodes, effectively plays each game 500 times, which is also defined parameter earlier. And so one change I made here was that normally, as you can see here, this is the state rewards and whether the simulation is done that the environment is passing back. I set right here these rewards to basically either always be +1 or -1. So any positive reward is +1, and any negative reward is -1. So the reason for this is that, for example, say in Space Invaders, you don't want to over-reward, hitting certain shifts or points at some points. You just want to associate, correct actions with negative actions. Particularly in Space Invaders, there's a case where there's a ship that will randomly occasionally fly up across the top of the screen, and then hitting that grants a large number of bonus points. So say, the model ends up hitting that really early on in training, and may get very biased and just keep looking for that kind of situation, or situations that might remind it of that, whereas in reality, that's a very rare random situation, so you don't want to overtrain on that. So by sort of cutting off these rewards and making them all -1 or +1, trying to sort of normalize this training and increase the likelihood that it converges on a correct strategy and does not, converge on a sort of incorrect strategy for situations that are not actually occurring very often. So, this loop is, effectively playing the game till it's done. And then for each episode, I am recording basically the run number, what the current randomization, aka exploration rate is, and then the score. And then I'm writing these to CSVs, one for each environmental learning rate pair. All right, so now we can get into sample results here. So we see a cart pull with a learning rate of 0.001. Cart pull is learned pretty quickly. The model, as you can see here, generally does pretty well. On the left side here, we see all the scores per run number. On the right side, we see the running averages, right? So we can see it's learned pretty quickly, and then generally keeps up here. Note, of course, this section we can see right here, probably from maybe runs about, say, 170 to 240 or so, the model performed very badly. So as discussed earlier, these models do occasionally struggle to converge on correct strategies. So the likelihood is what happened here is something happened in its training. It sort of converges on a local maximum that's not the correct strategy, so it performs very badly for a period of time until it sort of retrains and starts to reconverge on the correct strategy again. And you can see here we once again get very successful scores, and the scores once again rise. So as the learning rate increases, we see generally lower scores, approximately half throughout most of training, and many more of these clumps of very low scores. So what seems likely here is that the higher learning rate means that the model's not slowly converging on the correct strategy, but sort of rather jumping over from local maxima to local maxima, and then that's not actually very effective. And so that's resulting in these low scores for periods of time, and just generally lower scores. So moving on to Acrobat, we see pretty similar results here in general. With the 0.001 learning rate, the model has learned it very quickly. Stays generally up here, very, very good. With 0.003, many more very bad scores, and then generally worse scores overall. Again, it seems that the 0.003 learning rate is a little too high. The neural net's likely over-adjusting to certain stimulus and then not actually converging on the correct strategy, rather. Also, for the learning rates of 0.005, on both Acrobat and Carpool, sort of these dynamics were increased. Lower scores, more periods of bad scores. So moving on here to Space Invaders, sort of as hinted at a bit before, it generally struggled to train meaningfully on Space Invaders here. So even with the 0.001 training rate, these scores are effectively, it's pretty hard to distinguish this from randomness. And similarly with the higher learning rates, they look pretty much the same. And so it seems that this was just not enough time, especially given my hardware, to train meaningfully on Space Invaders. I do think it would eventually improve over time, given the improvements we're seeing on these other environments. But this was just not enough time to allow Space Invaders to train meaningfully. All right, so as a quick demo here, gonna show. So this is my model that's been training on Cartpole for probably about 20 to 30 minutes here. As you can see, it is clearly performing a strategy here. It's not performing randomly. It's clearly doing a very good job of keeping this cart pole balanced. The pole balanced on top of the cart. You can see it moving left and right. It's even trying to keep it centered because it's probably slowly associated that as getting to the left and right side of the screen is also a loss condition. Obviously, it's a slower loss condition than just letting the pole fall over, but you can see here it's hovering on the left and then coming back to the right. So you can see here that this model has clearly learned a lot of the strategy here in this game and is performing very effectively. You can see there it actually looks like a stop because it actually reached the maximum amount of time to balance the pole. So performing very, very effectively. All right, back to the presentation here. All right, so some conclusions here. The lower learning rates were generally more effective, seems to allow for the neural net to converge on more effective strategies. The higher learning rates seem to probably be overreacting or over-adjusting to specific scenarios encountered during training and not converging on most effective strategies. Even at lower learning rates, as noted before, the model occasionally does have periods of consistently low performance before readjusting and improving back to having effective scores again. And that Space Invaders was too complex of a simulation here. I even tried running it for 15 plus hours in some separate simulations, and it just would not show anything meaningful here. Likely, again, as would improve, but difficult to predict how much longer this would take. And so this seemed to be a little bit out of the scope of this project as a result. So some follow-ups would be to study lower learning rates as well. I noticed, of course, that here's the lowest learning rate was the most effective. So I'd be interested to see if that pattern continues with lower learning rates, or whether maybe it doesn't increase scores, but it just increases the amount of training time required. Just generally, what are the effects there? And then also I wanted to continue on sort of the questions that were asked at the start that were not quite able to be answered. How do higher and lower learning rates affect training across environments, varying complexity, and actually particularly I think levels of randomness would be very interesting. And my hypothesis here is that higher learning rates may be more effective with the more simple and deterministic environments because the model doesn't really, maybe run into rare or random scenarios and then overtrain on that. So you can afford to train a little more quickly on these simple deterministic environments. But that the lower learning rates are probably necessary for the more complex and more random environments to prevent the overtraining on rarely encountered situations. As we can see here, even with just Cartpole and Acrobat, some of the higher learning rates did create those problems. So my guess would be in comparing more complex environments, that kind of pattern would likely hold. Thank you very much. I hope you enjoyed this presentation on DQN networks and varying learning rates.